In this chapter, we'll deal in several sections with global positioning systems and related location topics. The objectives of the chapter include identifying and defining the key aspects of geographic data quality, including resolution, precision, and accuracy, explaining how radio signals broadcast by GPS satellites are used to calculate positions on the Earth's surface, stating the kinds of magnitude of error associated with GPS positioning, identifying and explaining methods used to improve the accuracy of GPS positioning, and listing and explaining the procedures land surveyors use to produce positional data. First of all, keep in mind that global positioning systems is part of the global navigation satellite system, which has to do with the use of satellites to fix locations on the Earth's surface. These are absolute positions, which may be then used and interpreted in GIS within the context of features and attributes. First of all, the U.S. Department of Defense developed the GPS system as the Navstar satellite system, navigation, time, and ranging, which is still the satellite constellation that's in use. GPS is technically specific to the U.S. system. The Global Navigation Satellite System is the generic name for the worldwide radio position, navigation, and location systems. Navstar became fully operational in 1994, and signals are available all over the world free of charge. Location is determined by signals transmitted from satellites. They're determined historical and vertical location, and they're based on atomic clocks on satellites. Signal travel time and velocity determine the distance from the satellite to the ground position. So it's very exact and specific time sinks and differences that are looked at. This is essentially a space version of triliteration. Later on, we'll learn a bit more about what triliteration is. In the first section of the chapter on geospatial data quality, validity, accuracy, and precision, these concepts are discussed in relation to data components. Where data precision has to do with the specificity of data, accuracy has to do with how much error, and relevance has to do with how the data appropriate for the task. Precision and accuracy are affected by errors. Error sources include human errors, instrument reading, faulty judgments, environmental characteristics like variations in natural environment such as temperature, gravity, the magnetic declination, and instrument errors which follow from the capabilities of the instrument, such as misuse of resolution. Resolution has to do with how finely an instrument can understand the sampling it's doing. So here's an example of resolution. This diagram shows the concept that resolution signifies the amount of detail measured by instruments or represented in depictions like maps and other graphics. High resolution would allow, for example, this grid cell approach to be more highly specific versus low resolution, which is less specific. And it shows the resulting recording of area on the Earth's surface. In the case of low precision, a larger cell. In the case of high precision, a smaller cell. And then precision relates to variation. Numerous measurements with low variation are more precise than those with a lot of variation. So less variation on the left means that you have less distance across the sampling area versus more variation on the right, greater distance. Don't confuse precision with accuracy. Precision is related to resolution and environmental variations. Accuracy relates to how close the measurement is to the true value. The difference is very important between the two. Precision has to do with resolution and the amount of variation that can be understood, while accuracy has to do with the truth of the data or the information being collected. Here are examples. Accuracy and precision are independent of one another. You could have high precision in the case of the diagram on the diagrams on the top, and accuracy may be a completely different issue. Two different types of error are systemic errors and random errors. Systemic errors follow a trend. They have a consistency in magnitude, direction, or they may be corrected using a constant factor, including additive correction. They may require a more complex adjustment called proportional correction. Random errors, on the other hand, follow no organized trend, and they may vary in both magnitude and direction. They may be difficult to identify and correct, and you may need to take an average of random points from multiple measurements in order to better understand random errors. And that concludes this first section of the slides related to GPS.